Good afternoon, everybody. You are looking live at Brad Keeler's backyard in Annandale, Virginia. I'm Brad Keeler, director of the Geo-Institute. Welcome to the second episode of GEOSTRATA Extra. Our first one was back in July. We had Scott Anderson on then to talk about data. And we're very happy today to have Farshid Vahedifard with Chris Woods talking about his article, Farshid's article, in this month's GeoStrata. For those of you who aren't familiar with the Geo-Institute, we're a membership society, an institute of the American Society of Civil Engineers with about 12,000 members, mostly geotechnical engineers and geologists. If you want to learn more, check out geoinstitute.org. We would love to have you. If you want to subscribe to our YouTube channel and see the other great videos that we have, click on the subscribe bell to get notifications up at the top, or find out more about us by clicking on our name and our logo down below this video in the description field. GeoStrata is our publication. We put it out 6 times a year, goes to all GI members. It's available in digital form on our website as well. You can go to readgeo.com to see more from that. Every article or every issue, we've decided we'll take one article, one piece, and do an extended interview with one of the authors from that. And that's why we are where we are today. So without any further hubbub from me, I will introduce Chris Woods from Densification, who's one of the editors of GeoStrata, and he'll be our host for today. Thanks, Chris.
Brad, thank you very much for having us. This is a great opportunity. As you mentioned, in July, we waded into uncharted waters to bring you the first ever edition of GeoStrata Extra, which was a very widely consumed interview with our own Mary Nodine and Dr. Scott Anderson of BCG Engineering and the FHWA, where they discussed big data and its adoption into geotechnical engineering practice. We hope to build upon, the success of that first interview, this content, with every issue, as Brad mentioned. For our second edition of GeoStrata Extra, we'll be speaking with Dr. Farshid Vahedifard. He's with Mississippi State University, and his article, Adaptive Infrastructure to Mitigate Future Climate Risk, was published in the current September-October 2020 issue, which has the overall theme of geotechnics of sustainability and climate adaptation. As Brad mentioned, my name is Chris Woods, the host of this edition of GeoStrata Extra. I'm Vice President for Densification, Inc., a specialty dynamic compaction contractor based out of the Washington, D.C. area. I've been an editor with the magazine since 2015 and an internet celebrity as of about 30 seconds ago. Farshid is the CEE Advisory Board Endowed Professor and an Associate Professor of Civil and Environmental Engineering at Mississippi State University in Starkville, Mississippi. Farshid's research focuses on the areas of geotechnical engineering that interface with resilient communities and infrastructure to extreme events under a changing climate. He also studies multi-physics processes in variably saturated soils. Prior to joining the faculty at MSU, Farshid was in the consulting world after completing both his master's degree and PhD at the University of Delaware. He has about 20 years of experience working in academia and private industry on different civil and geotechnical engineering projects. In academia, he has served as lead for 15 research projects with a total funding of over $5 million from NSF, DoD, the Army Corps, and private industry. He's authored over 150 referenced articles and is a recipient of a number of awards, including the 2019 ASCE MS Engineer of the Year Award, the Best Paper Award from ASTM Geotechnical Testing Journal, as well as the 2016 FLC Interagency Partnership Award. He also serves as an associate editor for the ASCE Journal of Geotechnical and Geoenvironmental Engineering and the ASCE Journal of Materials in Civil Engineering. He's a member of a number of technical committees with the GI and ASCE, including the ASCE Committee on Adaptation to Climate Change, where he was a contributing author to Climate Resilient Infrastructure, a manual of practice on adaptive design and risk management, which was published in 2018. On a related topic, but in absolutely no way a cross-promotional measure here with ASCE, he's also the co-chair of GeoExtreme 2021, which is a GI specialty conference to be held in Savannah, Georgia in August of 21. GeoExtreme aims to create a multidisciplinary forum to discuss how the geoengineering community can work with other professionals, climate scientists, engineers, emergency managers, resilience and sustainability investigators, insurance experts, and policymakers to properly cope with extreme events, such as hurricanes, floods, extreme precipitation, drought, wildfire, debris flow, earthquake, tsunamis, landslides, things of that nature. Pretty much everything we've seen in 2020 so far, changing climate. Farshid's article on how to adapt to climate change from an engineering perspective, in my opinion, really kind of makes you shift the way you think about the design approach. So as we move into things here, you're going to hear some great insights about designing for climate change. And I would encourage anyone having questions to fire away in the comments section. We'll address them as we go and as time allows. I do want to stress one thing, however. Climate change, extreme events are quite polarizing topics in this day and age. So with that being said, really the focus of this article was not so much on the hows and whys of climate change, but rather how we can better accommodate the effects of these changes as we need to design infrastructure that may have an expected service life extending to the end of this century and beyond. So just keep that in mind in terms of the questions that you're sending in. So with that, Farshid, good afternoon.
Good afternoon.
I guess most importantly, as we prepare to have this discussion here on extreme weather, how are you doing down there in the aftermath of Hurricane Sally?
Yeah, you're right. Good afternoon, Chris. Thanks for having me and for the great intro. Things are going well. As you said, the year of 2020 has been the year of extreme events. A combination of all natural and man-made extreme events has been good so far here, but we are preparing for the next hurricane, I would say. As you know, we are running out of the names for hurricanes. So it has been a pretty hectic year in terms of hurricanes and all other extreme events.
Yeah. Well, I guess let's just start off with this. I mean, some of the viewers out there, they may not have received, their copy of GeoStrata in the mail yet, and maybe they haven't had an opportunity to read the article. Why don't you just give us a summary of the article?
Sure. First, I wanted to thank you and the other staff members on GeoStrata. I was really impressed with the way that you guys handling the publication of GeoStrata. It was a very interesting and learning experience for me working with you all, and I was very pleased. About the article, as you said, what we are trying to do, we are trying to present a framework that we can adjust or design methodologies to deal with a changing climate, how we can have climate-ready infrastructure systems. And the first step from engineering perspective is to have a design platform that allows us to deal with those changes in the patterns of extreme events that we have been seeing over the past several decades, and we need to be better prepared for the future. So that's the main focus of this article. We are presenting a platform for a climate adaptive design, how we can adapt our infrastructure to deal with changes in extreme event while we are considering the uncertainty on any of climate projections that we have.
Okay. We're talking about design, and the intent of the article is design. From an engineering standpoint, particularly geotech, structural, one of the first things that comes to mind is code, design guide. So with the concept of your article being more of a, adaptive sort of change over time, not a hard and fast, approach, what are your thoughts on, how this type of approach can be incorporated into the design codes we use, such as, the predominant one that comes to mind for everyone is the IBC?
That's definitely a good point. If we want to take this approach into practice, in our daily practice, we need to implement it in our design codes. That's the way to go with this. As of now, we don't have, I would say, well-established design code with adaptive design approach. Over the past few years, there have been several studies or efforts trying to bring this perspective into daily practice. For example, some federal agencies like Federal Highway Administration have been trying to develop and use adaptive strategies for planning purposes, for design purposes. And also, as you mentioned in your introduction, as a part of the Climate Adaptation Committee of ASCE, we published a manual of practice back in 2018. And the goal was to provide a practical guideline for civil engineering community on how we can have a adaptive design for infrastructure. Here in the US, we are still working on it. Several agencies are working on it, but definitely we need to do more. There are some other countries that are ahead of us in this area. There are European countries that they have implemented adaptive design in Eurocode, so they're using it. But here in the US, other than few attempts, we still need to do more work on it. And that's something that we are trying to present here. You know, if you think about this overall idea, we deal with design, like on a daily basis in our, engineering world, in civil engineering world, or in geotechnical engineering world. And then when we are talking about climate adaptation, the first impression, this is not for me, this is too complicated, or this is just science. The point here is, no, it's not just a pure science. It has clear engineering implications. And that's how we are trying to build a bridge between climate science community, hydrology community, and geotechnical engineering community. Something that and I put in the title of the article, when I was working on the climate change community on adaptive design, something that I noticed and was very interesting for me was the concept of adaptive design in most cases is borrowed from observational method first proposed by Terzaghi several decades ago in geotechnical engineering. And that's why I said we are building upon our geotechnical engineering heritage here. So in geotechnical engineering, we are used to deal with uncertainty. We're dealing with underground. There are a lot of uncertain parameters. Soil, we know it's not a textbook material, so we deal with a lot of uncertainties, ranging from temporal uncertainty, spatial uncertainty, all kinds of uncertainties. The observational method first proposed by Terzaghi on how we can deal with kind of settlement problems for a long time, and as we learn more, how we can adapt with those changes. And the same concept has been used for climate adaptive design. And that was very interesting for me to see that observational method has been used by other areas in climate change community to propose an adaptive design. The key here is how, as geotechnical engineering community, can work with other areas, climate science, hydrology, risk analysis, and then have a unified platform that can be practical and can also incorporate the changes and uncertainty and offers flexibility in terms of design and in terms of the cost. So that's the whole idea that we are trying to propose, building a bridge between different disciplines in a practical way.
So, that brings up a lot of different points, right? You talk design, you talk cost. There's a lot of different aspects that need to be taken into this. One of the concepts of the adaptable design is just that, right? It's adapting to ever-changing climate events. So what kind of danger do you see in a scenario where maybe the upfront design, is conducted in a manner maybe not all the way to a worst case scenario, assuming that there will be further phases built on later as things change, but then all of a sudden something like 2020 happens, budgets fall apart, the money's not there, and maybe these additional phases of work are not, carried out or not able to be carried out. So what's your thoughts on that?
That's true. There are always surprises. That's the challenge, and that's a big one. In the context of climate change, when we design any structure, for example, when we design a levee, we are designing for a certain like a flood, or for like for any type of a structure that we deal with climate data. The thing is, over the past several decades, we have been seeing a noticeable change in the statistics of extreme events. And that's the notion that is called non-stationary, which means that we cannot use the statistics of past events to predict future events. That's the notion of non-stationarity. Now, the thing is, there is a huge variability and uncertainty in climate modeling and climate projections. This is not my area, and I've been actually I've been a user for the climate data. One thing that I learned, and I noticed that as time goes by, they're improving the climate projection models. So there is a huge uncertainty and variability. There are a large number of climate models, I don't know, 20, 25, 30. And among those models, you see a large variability. And the question is, if I'm a practitioner, which model should I use for my design purposes? And the change something is in order of magnitude, And
Right.
if I'm designing something that I need to have a flood level, which flood level should I take? Should I take it from this climate model, which is giving me something even below the historical, data, or the other climate model, which is giving me like twice as the historical data? This large variability can be very challenging to deal with that. What we suggested in this article is we have to have a risk-based platform. Based on the type of a structure, based on the importance of the structure, define a risk threshold, how much risk we can tolerate for that particular infrastructure. So we have historical data for that particular climate event, and based on climate models, we have a projection for future. So we have an upper bound. Of course, we don't want to go with upper bound in most cases because it will be very I would say conservative, or it will be over-designed. So the cost is a consideration, definitely. But between the historical data and the upper bound, where is the point that we have to start? We said the point to start with is defined based on the risk threshold that we define for that particular project. So the starting point is to define the risk threshold for the particular project that we are working on, that, which is somewhere between the historical data and upper bound from climate projections. And based on that risk threshold, start the initial design. And once you do the initial design, then think about, as you mentioned, to consider some adaptation capacity measures in your design. As an example, we use the levee design. We said that, okay, if I'm designing a levee cross section, it will be way more difficult to make changes in the geometry of riverside later on, compared to the land side. So for the land side, we have more flexibility, and it's easier to change the geometry later on if we need to. But on the river side, after levee is in operation, it's more difficult, particularly if levee retains water all the time. So on the river side, we can consider those adaptation capacity for any possible changes in the future. So that's what we call start with an initial design based on the selected risk threshold, and then modify the initial design by considering adaptation capacity for any possible changes in the future in areas that is more convenient to consider upfront versus waiting like 10 years and 20 years and then make changes later on. And then do the construction and keep monitoring the performance of the structure. And along the way, of course, we will have a better understanding about climate projections. The climate community, they keep improving their models and have their models output and the performance of the structure, and keep monitoring the probability of failure of the structure. If the probability of failure of the structure still meets the requirement, you're good. If not, see what modification we need to make. And that's what we call adaptive design.
Right. So, you bring up a lot of interesting points there. One is talking about the climate models, and, maybe it's just because it's what's on TV, but one of the things that comes to mind with me is, when we're watching the news, especially here on the East Coast, right? And you see these coming at us. You see they call them what, the spaghetti models, right? And it's like, you know, one model has it going into the Gulf, and the other model has it hitting Maine, and then they're kind of coming down. So I can see how that presents, you know, quite a challenge just from the pure engineering of it. I mean, how much confidence is there from what you're seeing, just from the design side of things, that information, that convergence, that those models are, you know, being used properly, being refined, and you know, really providing data that, you know, the engineering community can use?
In terms of the confidence about climate projection, this is, of course, outside my area of expertise. Those are something that climate modelers or, you know, hydroclimatologists that work on it. But what I can see from the climate models, there's a large variability among the models. Because, you know, if you think about it, we are talking about it like a global scale models, you know. They apply different forcing, and we have different, you know, they do projection considering different, you know, emission scenarios for future. If we are going to go with the current rate of, you know, emission generation, or we are going to reduce the emission. So there are, you know, conservative or more aggressive, you know, projections. So they call RCP, like different RCPs that we have, like 4.5, 8.5. So there is a large variability in terms of projections among the models, and in terms of projection among different, you know, emission scenarios that they have. That's why we need to find a practical way to deal with that uncertainty, and to make sure that our design is safe, and it's still it's something is cost effective. So that's a major consideration. And the way to go is to see what's the level of risk that we can tolerate on that particular project. If that's something life-threatening structure, yes, we have to be on the safe side. We need to be close to the upper bound projection at this point. But no, if it's not a life-threatening, and we can still be, we can still meet the project requirements in terms of probability of failure, we can be somewhere between the historical data and the upper bound. As time goes by, we learn more about climate projections, and also we learn about how the structure behaves under under different loading conditions and under different climatic variables that experience. So that's a live process, I would say. This is an interactive process that we have to keep monitoring. The key here is monitoring the performance of the structure, monitoring changes in the statistics of extreme event, then revisit the probability of failure of the structure, see if any change is needed or not.
Right. No, that's a good point. Maybe not a different way of asking the same question, because it's a different question, but like, you know, about the modeling, how things change over time. As we reflect back on, you know, infrastructure related failures and things like that have occurred during this recent time frame where you're referring to these billion-dollar events, right? You're referring to the increase in the frequency of billion-dollar events. Has there been, you know, go back and take a look at the designs that have occurred? Like, you know, you kind of the comparison you give in your article is robust design, meaning you're designing for sort of a worst case scenario, like your 100-year flood or your, you know, 500-year earthquake or something along those lines. The robust design versus this, you know, again, the adaptive concept where you're kind of looking back on failures. And, you know, one of the things that comes to mind right off the bat is the levees in Katrina, you know, things like that down in New Orleans. Like, there have been, you know, a lot of, you know, cases where that robust design was used and failure still occurred?
There are several factors here. First thing first, you're right. We have been seeing a noticeable change in the number of billion-dollar weather and climate disasters in the country. 2020 is the 6th year back-to-back that we have been having 10 or more billion-dollar disasters, and the year is not over yet. So just to give you a better perspective.
Yeah, this year can't end fast enough, huh?
Yeah, that's right. Since 1980, over the past 40 years, we have had 10 years with 10 or more billion-dollar disasters. Out of 10, 8 or 9 have happened since 2010. So, and there are several reasons for that. Part of that can be attributed to changes in, patterns of extreme events. That's one reason. The second reason can be changes in land use and land cover with all these, new buildings, urbanization, changes that we do in land. Those changes will cause more exposure, to hazard, make people more vulnerable to any damage. That's the other thing. I would add also aging infrastructure. This is another thing that we need to consider,
Right.
with those are different factors that we have to consider. And always there are some like other factors, unexpected factors like human errors or I don't know, some other unexpected issues with design or construction. So there are all different factors that play together. What we are trying to say here, we are trying to reduce those surprises, unexpected factors. Consider that what we had 40 years ago when we designed, for example, again, let's use an example of dams. The average age of the nation's dam is about 60 years old.
Right. Yeah, and that's, being here in DC, right in sort of the political epicenter of the, the country. I mean, that's always one of the things that's being talked about. What are we going to do with infrastructure, transportation? You hear the ASCE report cards, and the grades never seem to be very good in terms of the status of our infrastructure. So that certainly doesn't help. And to your point with the increase, I mean, all you got to do is look at the names of the hurricanes at this point, right?
That's
We're right through the Greek alphabet and into hieroglyphics because we're running out of all these things. Let's fall back for a second and touch more on the you use the word risk a bunch as it comes into play with the adaptive design concept. How do you foresee, I guess you have to apply like weighted, measures to things, upfront savings versus, damage, monetary loss is one thing, debt another thing, so how are all those, sort of factors weighed in on this adaptive design concept?
As you said, there are different types of, damages or losses that need to be considered. When we are talking about human lives, it's very different, things than, like a damage to like infrastructure. There are different methodologies on how you can quantify those damages. It depends on the function of the infrastructure that we have. In most cases, when we have human factor or human loss, then that's the point that we start calling the event a disaster. That human factor will make a big change. So that's why I said that if you have a life-threatening, like a critical, see what happened after Katrina. That wasn't just damage to infrastructure. It was also is a natural it was like a human factor or human loss was a major component. That's why that's what I said. I said that what we need to do, we need to consider what type of structure we are designing, what application we are designing, and what will be consequences in terms of damage to property, in terms of damage to the structures that we have, and if there is a human factor involved. Of course, we weigh more on that human factor or human loss, and that's how we basically try to come up with a threshold for risk that we can tolerate on that particular design.
Okay, so here I'm going to go. We have a question that's come in from our audience here. Sajjad Vaseji, his question for you is, in your opinion, to what extent is the engineering community, what willingness have you seen by the engineering community to incorporate climate change parameters into design?
That's a very good point, and based on what I've seen, there is a gap. There is, I would say, there is a resistance here. There are several reasons for this resistance to adopt that in daily practice. First, engineers, they think, it's too complicated, or it's not a real problem, or this is not for me, or the perception, I would say, the perception is, just recently, out of curiosity, we did a national level survey among civil engineering students to learn about their perception among resilience. And we were surprised with several fundamental misunderstandings about their perception about basic terms related to resilience. And all those civil engineering students, in a year, 2 years, will become, decision makers. They start working. And the thing to remember is we don't have a formal education system in place to teach them or prepare them to deal with adaptation, resilience issue. And when there is no formal education system in place, the perception plays a critical role, because all your decisions will be based on your perception. And if you think that's not a big deal, you want to spend time or resources. You treat that as a fancy problem. That's not type of thing that I do. That's the whole point that we are trying to make. This is not a fancy problem. As you said in the beginning, we don't discuss about causes, or we don't discuss about other debates over climate change or those kind of things. My point here is this is an engineering problem, and we need to define an engineering solution for this problem. We need to take a science-based engineering solution to deal with this problem. I'm not trying to say this problem is gonna destroy the entire country tomorrow. No.
Right.
And I'm not trying to say there is no problem whatsoever. I'm saying that, like any other engineering problem, if you are given to design a parking lot, you try to follow a certain, design codes or like engineering principles. The same thing if you are given like to design like, I don't know, like airport, like a skyscraper. The same thing, of course, more restricted. You will follow certain like principles, engineering codes to design them. The same thing here. The effect can be very critical in one region. It may not be as critical as in another region.
Right.
There is no one single prescription. It's again another design problem. It's like saying that I'm going to design a slope. Always use, I don't know, a slope of 1 to 3 for any slope. No, that's not the case. It has several factors. It depends on the load. It depends on the condition. It depends on the site. It depends on the geology of the site. It's the same thing. I'm trying to present it as an engineering problem. That's a very important point. We need to bridge this gap. I always, attend meetings and conferences by climate science people, and I always, enjoy learning from them. But one thing that I noticed that there is a noticeable gap between what they do and the implication of their work in the engineering community. And this resistance, this reluctance partly has to do with education and presenting in a practical way, so they understand, oh, this is another engineering problem that we can deal with that. As of now, I would say the engineering community has been, I would say, reluctant to adopt in like daily practice, and that's the area that we need to work more with education and with like this. With all different outreach activities to make sure that we understand this is an engineering problem that we can deal with an engineering solution.
Sure. So, yeah, I mean, you're right. I mean, you can argue till you're blue in the face one way or the other, like the hows and whys of all this stuff, but like there's not really much argument to the fact that there's how many hurricanes versus last year. Like that's just facts, right? And it is what it is. So, in the long term, then, kind of to build on your last point there, adapting and changing design, it never happens overnight. I mean, hell, just to, update a chapter of an already existing code, you go through X amount of committee reviews and people reviewing it, and just to make changes to something that already exists. right? So, these solutions, they're going to come from professionals, right? The professionals have to come up with the solutions to then work them into, codes, presumably through some sort of legislation, right? And then the approaches to how these solutions are then designed, exactly to your point, have to make their way down into college curriculum, So is this, what are your thoughts on this? Or are you seeing some sort of, bigger picture, approach coming in here as to how to work through these different steps?
You touched on a very important point, education. But I started myself. I've been working on this topic of resiliency and adaptation for the past several years. But as I think about my own, formal education, I never had like a course or like formal education about adaptation. I got my degree several years ago, but even today, we don't have any course, at least as far as I know, in almost, I don't want to make a comment about all civil engineering programs in the country, but about those that I know, we don't have any formal education about resiliency or adaptation, at least in civil engineering programs in most universities. And even take it further, I think it should be even before then. We need to have a better education for K-12, type of education. I'm not talking about too complicated terms. I'm talking about some basic terms. We need to know if there is a change, how we can adapt as a community with those changes, and then it will better prepare our next generation of engineers. It will better prepare next generation of decision makers. It will better prepare the next generation of, the stakeholders. That's the first step.
Right.
I think education is a key here. And if we can invest more on that piece, I think we'll have a much easier work to convince people to work together and deal with it as a science-based engineering problem.
Yeah, right. These concepts won't be foreign to people. You're right, because I think you mentioned there was like a survey done, like asking about resilience, right? I'm sure people in the geotechnical community would just look at that and say, "What does that even mean? Like, what are we?" Yeah. So we had another question come in, kind of more of a global, take on things. There are plenty of countries that don't necessarily have the political tension, that the U.S. does when it comes to climate change and their approach and things of that nature. So, in your experience with this and what you've been involved in to this point, are you seeing these other countries making more, not, aside from the U.S., making strides as it comes to incorporating climate into design, like we're talking about?
I would say, as I said before, there are some countries, for example, in Europe, they're ahead of us in terms of implementing adaptive design in their engineering practice. That's something that I can definitely say, and that's why they have it in their design codes, they have it in some of their design codes. In the U.S., regardless of controversial, discussions, there have been some, projects over the past few years trying to incorporate that into our engineering practice that I have to definitely mention them. As I said, Federal Highway Administration or like FEMA or Army Corps, they're trying to adopt, and they're trying to basically consider and use these recent, concept into their practice. But yes, there are some countries outside the U.S. that they're ahead of us in terms of taking that into daily practice, I would say.
So, with that in mind, have you seen anything that could even at this point sort of resemble a state of practice, so to speak, whether it's, elsewhere in the world or you give the FHWA, example, are you seeing, some sort of approach, along these different places that could be considered, similar or a state of a practice on this?
Oh, based on what I've seen, in most of what I've seen in other countries and also in the US, most of them, they're using a form of or a modification of the observational method that I mentioned. As I said, this ASCE Climate Adaptation Committee published a manual of practice back in 2018. There was a chapter in that manual of practice that we presented the adaptive design concept, kind of like a step-by-step procedure how we can use it, and there were example designs that can be used. But there are some countries that are already using it. That's what I call the state of practice. So
okay,
not here in the U.S., but there are some countries that are already.
So there's a little, I guess, my point. So there's a little bit of consistency, at least in some places then.
In some places, yes.
Okay. So, to me, we're talking, climate change. Again, I've lived most of my life on the East Coast of the United States, near the ocean, near the water. And I think for maybe a lot of people, maybe I'm taking liberties speaking for the people that live in things of that nature, but the first thing that always comes to mind for me when we're talking climate change is the discussion on sea level rise. And so then logically, the next step there would be waterfront. How does that impact waterfront structures, levees, bulkheads, those sorts of structures? So in your, taking a look at resilience and this adaptive design concept, I mean, what other impacts are should be considered? Levee storm events is again one that's there, but is there an approach to drainage design, right? You think of rain events and things designed to a 100-year flood or a 500-year flood. Like, how can you sort of quantify that? Wind loadings, hurricanes, are those things that are increasing and they're being considered? More blizzards, snow loads, things that act. So, I mean, how far does this kind of stretch in terms of the different specific type, wind, snow, water, things that are being, considered with this?
Yes, sea level rise, that is the first immediate trend that we can think of, and of course it will have direct impact on any infrastructure dealing with water, like along the coast, which we are talking about, like levee system. Regardless of sea level rise, we know that the nation's levee system is not in a great shape. Like dams, I would say they're pretty old, and we have a lot of several sections of levees that are not even, we call it federal levees or non-federal levees. We have a better statistics about federal levees, but there are a good portion of levee system that they're privately owned and maintained. Like levees were not supposed to be engineered structures. It's like a semi-engineered structure.
Yeah, right. Yeah, if you want an engineered structure to hold water, you build a dam, right?
Yeah, that's right. And then, but during the time, they become more and more important. They become kind of like a critical component of flood protection. Infrastructure system. So sea level rise is the first immediate thing that I would say. But there are several other climatic events that are changing and have direct implications in terms of geotechnical engineering or civil engineering design. For example, extreme precipitations. We use rainfall for design and also analysis. Over the past 56 years, overall in the nation, we have had an average of 20% increase in the amount of extreme precipitation in the country. This is the average for the entire country, but in some regions, like for example in Northeast, this increase has been as much as like 60%, over 60%. We had some regions with less increase, but for the overall nation, we have had 20% increase in the amount of extreme precipitation. Extreme precipitation, one thing. Flooding, I'm sure you have heard and you have seen, a lot of called like extreme flooding, like 500-year flood, 1,000-year flood.
Right.
They're not supposed to happen every other year, but
Yeah, right.
But we have been having a lot of them. And also one more event that, climatic event or extreme event that I definitely want to name is drought. Drought is, I would say, we sometimes underestimate the impact of drought or on infrastructure. When you say drought, people always think about the impact on like shortages in water resources. That's the immediate thing about drought. But drought can also have some major impacts on infrastructure, particularly geotechnical structures. The first immediate thing can be, think about desiccation crackings.
Right.
And we have seen very deep cracks in our levee systems after a drought season, and that those cracks can be a recipe for disaster when the next.
That's right. I mean, Mike Duncan was my professor at Virginia Tech, and his whole thing was always that water is bad, and so raging cracks, you get water in a day, you got problems, right? It's very logical steps.
That's right. And then we talked about all these single events. In most cases, they don't act as like individual events. We have a chain of events. There are more recent terms that have been used, like cascading events or connected events. Just as a very recent example, see what's happening in California, all the wildfires that they're having. If you go back a little bit, they had a 5-year drought season. Drought, right. After drought, you lose vegetation, and then it will make soils more susceptible to erosion, will make more fuels for, wildfires. And then, you have wildfire, and after wildfire, the next rain comes, and now you have debris flow. And then, it will continue like a domino. And
it's just a cycle, yeah.
Yeah, this is a cycle. That's what we call cascading events. That's another area that definitely we need to take into consideration. It's a very challenging task. How can we deal with cascading events when we are designing infrastructure? In some areas, like again, if we use California as an example, they also have earthquake on top of them, and some of these events, they may have interaction or relevance in terms of their causes, but sometimes they don't have relevance or connection in terms of causes, but they have connection in terms of their impact. That's the thing that we need to consider, like a flood combined with an earthquake, or like think about this wildfire season. We did a study back in 2018 before this deadly year of 2020. As of now in California, they have by far the worst year in terms of wildfire in 2020, and the fire season is not over yet.
Right.
What we studied was first, of course, we see a very significant increase in terms of the area, the burn area. One more interesting trend that we saw was the elevation of fire is going up. Why? Because of the changes, snowpack. That's why fire elevation is going up, and because of drought and changes, snowpack, and now you see fires going higher and higher in elevation. That's why you see this like a domino effect, and it's causing. And then they had the next rain, and that they had this deadly mudslide. I think it was back in 2018 or 19, which was after the fire that they had. And this year, now they have all these fires going on in California. I'm sure it will be a lot of major mud flows or even like landslides, followed by this fire season that they should be prepared for.
Absolutely. No, and that was one of the next questions I wanted to touch on, everything going on with these wildfires. It's been interesting sitting here in Virginia. The last week we had like yellow hazy skies because of, the effect of the jet stream bringing all that smoke across the country. And, you could feel the effects of it here, right? So, that cycle, fire, then drought, then, extreme rain, which leads to mudslides, this sort of, it goes on and on and on. Is there, something in your mind or an example of like how you could sort of even begin to address something like that cycle as it comes to design?
That's a good point. We recently started working on a design platform when we concurrently consider the risk of earthquake plus flooding. In the West Coast, this is a very dominant problem. How we can consider joint probability. That's something that we need to consider. Yes, there are ways that we can incorporate that, and that's something that we can consider multiple events and then consider the interaction of multiple events. And based on the connection and the interaction between multiple events, then design your structure to deal with those multiple events. But of course, we need to make some changes. As of now, as far as I know, we don't have a code or design code that consider multiple events, or if we call it cascading event or connected events.
Right. So let's go to, we got, a couple more questions before we wrap up here. This is more of a theoretical question, but, how can, nature's own capacity, be used to deal with climate change? Is there, examples of, how nature can inspire, some of these more adaptable designs?
That's a very interesting point. We have this concept of engineering with nature. Mother Nature always, has the most stable configuration for anything. And the problem is that as soon as human beings start touching, disturbing Mother Nature, that's the problem. And in most cases, those interventions cause issues. In terms of using nature's capacity for adaptive design, I would say that's possible. As I said, one of the main reasons for the trends of higher, number of billion-dollar disaster is changes in land cover and land uses. If we can, restore some of those changes, of course, I'm not saying that, stop urbanization or like building, but there are some we can, think about like rivers or ecosystem in some parts that can have direct impact. But that's a good point that definitely needs more studies, I would say.
So we got one last question here before we wrap up. The question is basically that, structures are being designed for longer periods. So I don't know if that goes down the road of maybe the more robust design, but is there a consideration for, instead of a typical, 20 or 50 year designing for 120 years or designing for longer periods of time? Like how does, in terms of material parameters or, any of those sorts of things? Is that something that's playing into this adaptive concept as well?
That's definitely a good point. When we design infrastructure, as you know, we generally design for in terms of loading condition. When you're talking, for example, flooding, depends on the type of structure. We design for 100-year flood or 200-year flood. If we can update or flood, flood maps or floodplain maps or the statistics of flood, then we can use that updated flood data in our design. That will address that part. For example, we did a study a few years ago. We looked at the changes in the extreme events. We noticed that not only change in the intensity of rain, we also noticed that the frequency of extreme rainfalls is also increasing. So if we have updated, downscale the statistics of extreme events, we can incorporate them into design, considering changes in intensity and also frequency of those extreme events.
Interesting. Well, hopefully, our viewers out there have had a chance to kind of wrap their head around the concept, and it's something that I don't think anyone, thinks is going away anytime soon, for sure. So, first I'd like to, everyone that took their time out of the afternoon to join us that's out there watching. Farshid, this has been a great experience for me, getting to know you a little bit, having this conversation. So I, appreciate the opportunity to talk with you about this. So if you have any, last remarks or whatever, and then we can turn it back over to Brad to wrap up.
Sure. First, thanks, Chris. I enjoyed the conversation. Yes, this is the topic that we have to live with it. And I hope this article or this conversation can be a small step toward, attracting more attention to this topic in our community. Other than that, no, there's no more point. But I would like to thank you and Geo-Institute for having me for this interview.
Absolutely. Great. All right. Well, with that, Brad, we're going to kick it back to you.
Thanks, Chris, and thanks, Farshid. This was really good. Always a hot topic. I got to tell you, when I was an intern many years ago, I worked for the Canadian government in the Department of Science and Technology. And the first time I went to anything on climate change, this was 20 years ago, I thought, man, something along the effect of, it'll be great when we figure this out in like 10 years. And here we are. It's been 20. I think it's going to be another 20, and we're probably still going to be having the same conversations. I feel like it's one of those things like energy. There are always going to be questions around it. What you have to zero in on are the things that are always going to be there. Like with energy, it's storage and transmission forever and ever. Those are the questions. So with climate change, I feel like it comes with its own set of issues. We can get distracted by these little points off to the side, and that's what happens a lot of the time. But you guys really hit on some of the underlying concepts today that make this a big deal, and hopefully we can start reaching some of these solutions for humanity. Sounds very big and grand, but it really does affect everybody on the planet. So thanks also to Aaron Harover on our team at GI for setting this up and making it work. We wouldn't be streaming if it weren't for Aaron. So
that's right. Thank you, Aaron.
Thanks.
Please join us for our upcoming streams. We'll have one on Thursday on the IDEA program for MSc Walls that we maintain. It'll be on sample IDEA evaluations. That's at 1 p.m. Eastern on Thursday. Join us for that. Next Friday comes only once a year, Terzaghi Day, October 2nd. Carl Terzaghi's birthday. He would be 137 this year if he were still alive. We will celebrate virtually. We will have ASCE President Guna Gunalan joining us at 2 p.m. Eastern on Friday on YouTube Live, talking about how Terzaghi impacted his career and the legacy of Carl Terzaghi on the profession. So you want to join us for that. You can find lots more good content on our YouTube channel. As I mentioned at the beginning, click on our logo. You'll get all our videos. This one will be up as soon as we're done here. It'll be archived forever. So if your friends couldn't make it to this one, tell them they can come back and watch it a zillion times if they want to. And other than that, I think that's it today. Thanks everybody for being with us. Thanks for your questions. You helped make it a great discussion, and we hope to see you soon.
Thanks.